Hey guys, so we're checking out grade 12 math paper 2 June 2025. In the diagram below, A, D, Q, C and DPB are straight lines. D is a point on the y-axis, A and B are points on the x-axis. The equation of line BC is y equals 2x minus 24 and the equation of line AC is 7y minus x equals 14. It is given that P is 6 and 1, we got Q is 7 and 3, T is k and negative 1 and TP in terms of length is the square root of 293. So calculate the gradient of PQ. So PQ is over here. So our gradient formula, M equals y2 minus y1 over x2 minus x1. So 2 marks, they're just getting us started. So we got y2 is 3 minus 1, then we got 7 minus 6. Just keep in mind that if you started with Q's values in terms of y, 3 and 1, and then x, 7 and 6, we have to keep it that way. If we started with P and then Q, that's fine, as long as we take them in the same order, the Y, 1 and 3, and then the P, 6 and 7. So at this stage, we can just calculate them. We got 2 over 1, therefore the gradient is 2. So then 1.2, it says give a reason why PQ over here is parallel to BC. So it's 2 marks. We just calculated that this guy is 2 in terms of gradient, PQ over here, and they have given us the straight line equation of BC. So we're proving PQ parallel to BC because they both have a gradient of 2. The 2 that we have is here in the straight line equation for BC, and then PQ, we calculated correctly that it is 2 as well. So therefore, M of BC equals the M of PQ, 2 equals 2, therefore PQ is parallel to BC. And we just earned 2 marks there. So the next question, if Q is the midpoint of DC, so Q is over here, calculate the coordinates of C. So we need this guy over here. We need its X and its Y coordinate. We don't have them. We have the Q here. We have the X and the Y over here, and then we just need D's coordinates. So this is a 4-mark question using midpoint working backwards, but we don't have D just yet, but we can just manipulate this guy in order to calculate D's coordinates. Because if we rearrange this in standard form, we have 7y equals 14 plus x. I'm just going to divide it. So I'm going to go 1 over 7x. So I just moved the x here, and then I divided by 7 plus 14 divided by 7 is 2 over there. And then this guy over here is the y-intercept over here. The x value is 0, but now we know due to this y-intercept that our y value is 2. So we have 0 and 2 here, and then we need x and y. Then we just have to work with our midpoint formula backwards. Okay, so the midpoint formula, we're going to treat x and y separately. So I'm just going to say MP of x over here, x1 plus x2 divided by 2. And then over here we have MPY equals y1 plus y2 divided by 2. So at this stage, our x value for the midpoint is 7 over here. Our 1x value is 0 that we calculated for D, and then the other x value is what we want. So we have 0 plus x over 2, and then we can just solve for this quickly. Times the 2 up, we have 14. 0 plus x is x. So we have 14 here. And now MPY, calculating that, we have 3 as the y value for our midpoint. Y2 is 2 over here, plus the y that we want. And then we divide by 2 times the 2 up there. So we got 6, 2 plus y, and we can take the 2 over, and then y equals 4. So our coordinate pair there is 14 for our x and 4 for our y. Okay, great. So this is a 5-mark question over here saying calculate the size of ACB. 5 marks, ACB. So we want the angle here for C. C had the little hat on over here, which meant that was our angle connecting A, C, and then B over here, which means this angle here is a question mark. When we are in our analytical geometry section, the most common way to get any sort of angle is doing M equals tan theta or beta if we are working with this guy. And the most common way to get an angle that is not on the x-axis, because this formula only works on the x-axis, is to do some sort of interior angles of a triangle. Because what we do have is we have theta over here, which means we can unwrap and get the angle using m equals tan theta. And this gradient over here, we had the gradient already actually, was y equals 1 over 7x plus 2. We had that from our previous calculation, which means we can get the angle here using m equals tan theta, making this tan theta equal this gradient over here. Then what we can also do is get the angle of inclination off of the x-axis to get beta, based off of the fact that we know the m here for the straight line equation as well. So once we have this angle and we have that angle, then we can do exterior angles of a triangle, because this whole of beta will equal theta plus c. And then that guy will equal our beta, and then we can work backwards and get our c value. Cool. So we'll take it step by step now. So what we have for this first theta is 1 over 7 equals tan theta. So then in our calculator, we're going to shift tan 1 over 7, and then we're going to get the angle for that. And we have 8,13 for our theta over here. So then we can do the same thing for beta. So m equals tan beta. And then what we do is we make this guy equal 2. So 2 equals tan beta. And then we can shift tan this guy and see what the value is for beta over here. And we have 63.43. So now beta equals theta plus angle C. So we can just write that down. Beta equals theta plus angle C. The reason is because of exterior angle of a triangle. So 63,43 equals 8,13 plus C. We have these guys, and then our final answer for C is 55,30. So now we have question 1.5. It says calculate the area of quadrilateral BODC. Okay, so we just calculated angle C over here. That was 55,30. So they want the area of quadrilateral BODC. Okay, so this irregular looking shape kind of looks like a kite a little bit, but we aren't entirely sure. So we have a couple of options. This is a 4-mark question. So we have two options here. We can either get the area of this triangle and add it with the area of this triangle. So we can either do that, or we can get the area of this big triangle here, ABC, and then we can subtract DOA from there. So I like that method a little bit more at this stage, especially because of this right angle triangle on our Cartesian plane. So a reminder that our values here for D was 0 and 2, and our equation for this guy was 1 over 7x plus 2. So we have the equation of this line, we have this angle, a reminder that this value here was 14 and 4. This is all information we had previously calculated, which we can use as we progress. So that means calculating the area of quadrilateral BODC. What we are trying to do here is to get the area of ABC and then subtract the area of AOD from it. So what we first have to get is the coordinate of A and the coordinate of B, because we don't have that. So we'll want this side. So in order to get the coordinate of A, we're going to have to let y equal 0 for this guy. So if we let y equal 0, we have 1 over 7x plus 2. We take the 2 over, we have minus 2, 1 over 7x, and then we can times this up, which means we end up with negative 14. And that is the value of x over here, which means this value over here is negative 14 and 0. And then for b, what we can do is the same thing. So this guy over here, we make that equal 0. So 2x minus 24, great. And then what we can do is take the 24 over. We have 24 over there. We have 2x over here divided by 2, and then this x value is 12, which means b is 12 and 0, which means the whole length of AB, considering it's on the same horizontal, is 26 units. So AB over here equals 26 units. This is good for us because remember, we want half base times perpendicular height. Okay, so we have the base over here, but we only have a hypotenuse and we have kind of a slant height. But one thing that was good earlier was that we had this perpendicular height if we connected this triangle over here. This perpendicular height, the maximum height of this point, is 4 units over here, which means we have half times 26 times 4, which is the perpendicular height over here. And then we can calculate it, and then we have 52 units squared for the area of triangle ABC. Okay, but then what we want and what they asked for is BODC. A reminder, BODC is over here. We're just going to subtract the area of AOD from this triangle, which means getting the area of this triangle is quite nice because it's negative 14 all the way to 0. So we already have the base over here, and we have the perpendicular height because the perpendicular height is all the way up to 2. So in triangle AOD, we have half base, a reminder base is 14 units, times 2, because our perpendicular height is OD. OD is 2 units up. And then what we have is 14 units squared, which means what we're left with was this guy we just calculated, and then we calculated this whole thing over here. I'll erase all of that now, which means once we subtract this portion from there, we are left with OBCD, and that is what we want. So then last move is saying 52 units squared minus 14 units squared, and we are left with 38 units squared. And that is our final answer. Cool. So now we're on question 1.6. It says if TP equals the square root of 293 in terms of length, determine the value of K, the value of K over here. So this is only 3 marks, which means it's plugging into one formula. So we have the distance of TP. A reminder that all of these are on the formula sheet. We have our distance, our gradient, our midpoint, and the equation of a straight line. So we have our distance of TP, that is the square root of K minus 6 squared plus minus 1 squared. And then we can just go ahead and solve for it. A reminder that TP was the square root of 293 because we're trying to solve for K here, which means we should and we have to know every single other thing in this equation. So TP was the square root 293. And then the nicest way to approach this line is to square both sides, to unhat it. So we have the square root here. We have K minus 6 squared plus minus 2 squared. And then we were just squaring here and squaring here to drop the square root on both sides. So we have 293 over there, and then we have K minus 6 squared plus minus 2 squared is 4 over here. And then we can take the 4 over, which means we're left with 289 over there. And then what we have to do, we're going to have to expand our K here. So we're going to have K squared minus 6K times 2 is minus 12K. Negative 6 times negative 6 is positive 36 over here. And then we're going to take this 289 over. We have K squared minus 12K. 36 minus 289 is minus 253. And then we can go ahead and we can factorize this. So quite a few moves for 3 marks at this stage, but only one value will be true because this quadratic equation will give us 2 values, and only one of these values will be negative and in this quadrant where we have a negative K. If we have a positive K, that is incorrect, and the value here has to be negative for the K. So instead of just factorizing normally, I'm going to use the quadratic equation, and then we can get our 2 potential values of K. So therefore K equals 23 or K equals negative 11. And a reminder, only the negative value can satisfy this equation. Therefore K cannot equal 23, and this will be our final answer for K. So then 1.7 for 2 marks, it says E, A and B is a point in the second quadrant such that A, B, C, E is a parallelogram. Determine the values of A and B. So E, A, B is a point in the second quadrant such that A, B, C, E is a parallelogram. Determine the values of A and B. So I haven't drawn this to scale, but a reminder that the main thing to look for parallelograms is whether the midpoints bisect, which means the midpoint this way will equal the midpoint that way, which means D is the midpoint. So we have coordinate A. A reminder that coordinate A was minus 14 and 0, and B was 12 and 0 over here. C was also 14 and 4. So we can do inspection at the stage if we want to, but the easiest way is to use the midpoint, the fact that D is the midpoint. So we can just do our midpoint formula working backwards. D's coordinate was 0 and 2, and then we can just unwrap this going backwards. So 0 is the x midpoint equals 12 plus x of A divided by 2, which means 0 times 2 is 0, and then minus the 12 over, we have minus 12 equals the x of A. And then we can do the same thing for y, and then what we're doing is we're making 2 equal 0 plus y over 2. Because this was our 0 here, this was our midpoint, and then we need the other value over there, which means we have 2 times 2, and this goes up to 4. So therefore, YB is 4, the XA is negative 12. And then we have the values of A and B, and E's coordinate pair is minus 12 and 4. Cool. And then question 1.8, the last question of this section. Determine the equation of the line which is perpendicular to AC and passes through Q. So it is perpendicular perpendicular here and passes through Q at 7 and 3 as the coordinate pair. Okay, when something is perpendicular, the first thing to remember is that m1 times m2 equals -1. By that, I mean the gradient of AC times the gradient of this new line will equal -1. So we already had the gradient of line AC. That was y equals 1 over 7x plus 2. We calculated that in one of the previous questions, which means 1 over 7, a positive gradient, times m2, this gradient that we want, equate to -1, which means we can just divide this 1 over 7 here, which means we have -1 divided by 1 over 7 equals m2 over there, and therefore the gradient of m2 is -7. So it is a steep line, it is negative, decreasing from left to right, and that is our gradient there, which means we're just one move away from getting the equation of the line, because y equals mx plus c over here. So we have the gradient, it is -7. All we need to calculate is a c value, and they've given us the coordinate q, which is the x and the y that we need to plug into this equation in order to get c, which means we have -7 times 7, because that is the x value. So our y value is 3 over here, and then we are calculating c over here. So -7 times 7 is -49, and then 3 is over here plus c, and then we can just take our -49 over, it becomes +49, and 49 plus 3 is 52. And that is the value of c, which means our equation of the line that is perpendicular to AC is y equals -7x plus 52. And that is our final answer here for 1.8, earning us 25 marks for this whole section. Cool guys, so question 2.1, it is saying in the figure below, the line 2x minus y plus 1 equals 0. Okay, 2x minus y plus 1 equals 0 is a tangent to the circle with center M, A and B at G, 2 and 5. They've drawn the 90 degree over here, which is going to help us considering a tangent is perpendicular to the radius. That is a Euclidean rule. The center of the circle lies on the line x plus y equals 9. So we have this line over here. So 2.1.1, determine the gradient of GM. Only 2 marks. So the gradient of GM has something or everything to do with this line, because we don't have the coordinate m yet. That is only coming up later, which means we have to manipulate this straight line equation and then do the m1 times m2 equals -1, because this gradient over here, once we unwrap it, our y over there equals 2x plus 1. So this line is 2x plus 1 is the intercept over here, 0 and 1. And then what we have is a gradient of 2, which means 2 times m2 equals -1. And then divide by 2, which means m2 is -1 over 2, which means the gradient of GM is -1 over 2. And that is our final answer. So then 2.1.2, it says determine the equation of GM in the form y equals mx plus c. Also only 2 marks here, which means we have to just plug in this gradient we calculated into this equation and then plug this x and this y coordinate into there. And then we can solve for c, and then we can have our equation. So y equals -1 over 2 x plus c over here. And then the y value is 5 over there, equals -1 over 2 x is 2 over here, so we can plug that in, plus c. What we have is -1/2 times 2 is -1, 5 is over here, plus c is over here. Take our 1 over, c equals 6, and then therefore y equals -1 over 2 x plus 6. And that is our final answer. And then question 2.1.3 over here, calculate the coordinates of M. So we need M. M is a point on this equation, GM. A reminder that we just calculated the equation of GM, or determined the equation, for an important reason. These are all follow-on questions, which means GM and this tangent over here, this guy with the equation of y equals -x plus 9. M is the one point in time where GM and this line going through here intersect, which means we can just make them equal each other, and then from there we can calculate the coordinates of M. So what we do when we equate them, a reminder that our equation for GM was y equals -1 over 2x plus 6. So then we're just going to make this guy -1 over 2x plus 6 equal this other line over here, equal the -x plus 9. So at this stage, we're going to take the more negative value over. So we're going to have 0.5x over here, and then we're going to take this positive 6 over there, and we're left with 3 over there. And then if we divide by a half on both sides, we end up with a value for x, the a value over here, as 6. So that is what we achieved by equating the two graphs. And then we need to go ahead and plug in the 6 into either one of these graphs to get their y value. So if we just plug it in here into y equals bracket minus 6 over here plus 9 equals minus 6 plus 9, we have y equals 3 over there, which means our equation over here for m is in coordinate form 6 and 3. Cool. And that is our final answer. On the memo, it said that if we didn't put it in coordinate form, we would lose a mark. So just a reminder that whenever they ask for coordinates, put it in coordinate form. And then question 2.1.4, hence or otherwise calculate the length of the radius of the circle. Okay, so the length of the radius of the circle. So we just calculated A was 6, B was 3, which means we can just do the distance formula for GM, and then we can have the distance, the length of the radius, because GM is the radius of the circle. So then our distance formula, distance squared equals 2 minus 6 squared plus 5 minus 3 squared. And then we're going to solve some values. We're going to square root this as well. So we're going to square root it. So we just have the radius. 2 minus 6 is minus 4. Minus 4 squared is 16. And then this guy here, 5 minus 3 is negative 2. Negative 2 squared is 4, which means we have the square root of 20 over here, which is the same as 2 surd 5. And we can leave our answer there, or we can simplify it to 2 decimal places. Either way is good. This question was leading very nicely into this next one. 2.1.5, write down the equation of the circle in the form x squared plus y squared plus cx plus dy plus e equals 0. So just 3 marks. They're asking for a specific form, but a reminder that on our formula sheet, we have the equation of a circle. So x minus a squared plus y minus b squared equals r squared. So we just calculated r, and then once we plug in our a and our b, a reminder that our a and our b was this guy and that guy, as well as the r, and we FOIL everything out, we can move everything to one side, and then we will have it in a form like this. So x we're going to leave there. So x minus a, remind our a value was 6 over here, plus y, our b value was 3 over there, squared, and then r was 2 surd 5, 2 surd 5, and squared, which means we can just go ahead and start to expand everything, take it to one side, and we will be done. So x times x is x squared, minus 6 times x times 2 is minus 12x, minus 6 times minus 6 is positive 36, y times y is y squared, minus 3 times y is negative 3 times 2 is minus 6y, and then negative 3 times negative 3 is positive 9. Okay, and then 2 surd 5, that squared is 20, which means we can just simplify everything, taking it over. I'm already going to start putting it in the form that they want, with the x squared first, then the y squared following. And then from there, a c and an x. So we have minus 12x. There were no other x's to simplify. A d with a y, so minus 6y. And then plus e. Plus e has no coordinates, which means it's our positive 36 here, our positive 9 over here, and this 20 here. When we take it over, it'll be negative 20. So we can just simplify them. 36 plus 9 is 45, minus 20 is plus 25. And that all equals 0, which means we have it in x squared plus y squared minus cx plus dy, which is also minus dy, plus e, the value without any x's and y's on it. Cool, guys. And that is our answer there. And then question 2.2 over here, it says determine the equation of the inverse of the tangent to the circle. So we have x squared plus y squared minus 26x plus 12y plus 105 equals 0 at 7 and 2. This is not the same circle. This is a different circle now. This is the equation for our previous circle, and they had different values in terms of x, y, and the e value, the value without any x and y. So this new equation, or this new circle with its own equation, intercepts at 7 and 2. Okay, so that is the point on the circle. And then it says, give your answer in the form of y equals mx plus c. So this is a 7-mark question. So let's break it down step by step. So what we need to do is first get this in some sort of standard equation form like this: x minus a squared plus y minus b squared equals r squared. Because right now this is all messy and we need to simplify it a bit so we can figure out another point on it. Because right now we only have the one coordinate pair, and in order to get a gradient at any stage we'll need 2 coordinates. So we don't have 2 coordinates, but a way that we are going to get the other coordinate pair is by factorizing it, completing the square, so we can get our a and our b, the center of this circle. So I'm just going to rewrite this equation here. We have x squared plus y squared minus 26x plus 12y plus 105 equals 0 at 7 and 2. We want our answer in the form of y equals mx plus c. So that's our question mark. This is our end goal, and then 7 marks. So first things first, in order to get the a and the b value, like this previous equation up here, we have to complete the square. So we're going to rearrange this equation by putting our x's back together, our y's back together, and then taking our r over to this side. So what we're going to do is take this positive 105 over. It is minus 105 over here. And then we have x squared minus 26x. I'm just going to leave some space so we can complete the square, plus y squared plus 12y. So that's a little bit neater. We have the x and the x over there. We have the y squared and the y over here. And we took our 105 over. So we aren't in this form yet, but we have an r in one place at least. So now what we have to do in order to get our bracket, the x minus a and the y minus b, we're going to have to complete the square. And in order to complete the square, what we do is we divide this guy by 2 and then we square that value. So what that means is we have x squared minus 13x, and then 26 divided by 2 is 13. 13 times 13 is positive 169. So we divided this term by 2 and then we squared it. So we left with 13 and then we squared that value and we put it here without an x, because now we have a nice grouping that we can turn into a bracket like this guy. So then we do the same thing over here. 12 divided by 2 is 6. 6 times 6 is 36 over here, which means we have a nice bracket over here where we have our 6y over here. 12y divided by 2 plus 36 over there equals minus 105. But we're not done. One thing we have to keep in mind is that what we do to one side of the equation, we have to do to the other side of the equation. We're just trying to change the formatting, not the meaning. By that, if we added a positive 169 here, we have to add a positive 169 over here. And if we added the positive 36 here, we have to add a positive 36 to this side. The right side needs to get the same change as the left side. And then at this stage, we can just package this guy up by going x minus 13 squared. If we were to FOIL this and SMS this, we would end up with the same bracket here. And then what we do is plus y plus 6 squared equals, and then we just have to simplify this whole right side. And that all equals positive 100. So at this stage, we have our format. A reminder that this is r squared, which means our radius is just 10 over here, but we have 2 new coordinates that we can then just use to help us get the gradient. If we had a circle like that, we would then have some sort of tangent going to the circle, something like this. Because now we have this coordinate here, this a, this x value for the center of our circle, and this b value, the y value for the center of our circle, and we have this other coordinate pair over here on the circle. So in order to get m, we are just going to use the gradient formula. So we'll have m equals y. So let's go 2 here, minus 6. A reminder that if there's a positive inside our bracket, it means it is shifting us to the left into the negative land, which means we're somewhere over here in terms of y. And then our x is 7 minus 13, because a reminder that if we have a negative x here, it means we are shifting 13 units to the right. We have some circle, something like this over here, with that being the center of our circle. So now we have this equation set up for our gradient, so we can just calculate it. A reminder, we used the points 7 and 2 over here that was on the graph, as well as the values for the center of the circle, which means 2 minus 6 is 8, 7 minus 13 is minus 6, and then this equals negative 4 over 3. But a reminder that this is just the equation in the circle from our radius to a point on the graph. So let's say something like this, because it's negative 4 over 3. This was our center over here, which was 13 and -6, and this was a point on the graph of 7 and 2. That's not looking like 7 and 2, so that's not necessarily where it would be living, but we're just going to put it there for now. So what we need then is the equation of the inverse of the tangent. So we're not dealing with the inverse yet, but we are dealing with a tangent, because just like this guy where we came from a tangent had a perpendicular gradient to the radius of the circle, which means we're going to have to take this -4/3 times by m2 and make it equal -1, because our tangent is 90 degrees to this radius. So we have that guy over there. So that means our answer for our gradient of our tangent is 3/4. And we've just earned 4 marks. We have the gradient of the tangent, but we don't yet have the equation of that tangent, which means we first have to deal with that before we deal with the inverse. So what we have to do is we're going to go y equals 3/4 x plus c over here. And then this tangent does not go through this 13 and -6. It isn't the radius, but it does go through 7 and 2, this point on the circle. So therefore, we can plug in the 7 and 2 over here into our x and our y value, which means we have 3/4 times 7 plus c, and then our y value was 2 over there. So we can just simplify this. 3/4 times 7 is 21/4 plus c equals 2, and then 2 minus 21/4 equals -13/4. And that is our c value, which means y equals 3/4x minus 13/4. Okay, but we're not done, which means the final mark is to do the inverse of it, because the inverse is bridging a paper 1 word that we know. When we do the inverse, we swap the x and the y value, which means what we have to do here is first get our x and y a little bit neater, because right now they are mixed fractions and that's not great for us. So if we multiply everything by 4, because there's a common denominator of 4, we have 4y equals 3x minus 13. This makes it a lot neater for us to then swap our x and our y, because we are getting the inverse to this tangent, which means we are swapping the x and the y here, which means we get 4x equals 3y minus 13 over here. And then from there, we can just isolate for y, because we want the equation of the inverse. And then that means we still have to isolate for the y, which means we'll take this -13 over here. We'll end up having 4x plus 13 equals 3y. And then we end up with 4/3x over here, we're dividing by 3, plus 13 divided by 3, and that equals y. And that is our final answer, getting the inverse for the tangent to this circle. And we have gotten it in the form of y equals mx plus c, and we have just earned 7 marks. Cool, guys. So 3.1 usually starts with something like this, where we have to do some sort of construction of a triangle. So we have tan beta equals 3/4, and then it says where beta is an element of 180 degrees to 270 degrees. So it says with the aid of a sketch and without the use of a calculator, calculate this. So 3 marks isn't for answering this guy so much, but a lot of marks are given for the construction. So if we have tan beta over here equals 3/4, a reminder that we have SOHCAHTOA. So we have sine equals opposite over hypotenuse, our cos equals adjacent over hypotenuse, and then TOA is opposite over adjacent. So we have that, or we have SYR, TIX. So SYR-CXR-TYX, or shelter your rear because X-rays tan your exterior. Okay, so these are the setup as far as what this means. Because right now we have tan beta, which means we have the y over the x. Okay, that's very good for us as far as the construction that we're headed towards. And then we have a positive tan over here. Okay, so if we are doing our construction over here, this is our cast diagram, where only cos is positive here, all of them are positive here, sine, cos, and tan. Only sine is positive here, and only tan is positive here. So this is telling us tan beta equals 3/4, and tan beta is positive. So tan is positive here, and tan is positive there. And then they've given us this restriction over here, where beta is an element of 180 degrees to 270 degrees. So we have 0 degrees, we have 90 degrees, we have 180 degrees, we have 270 degrees. Okay, so that means element of 180 to 270, it only fits in this quadrant here, which means we are just dealing in the third quadrant, and that is where we're going to do our construction. So now that we have figured out the values of our y and our x, we figured out which quadrant we're going to construct in, we can go ahead and we can draw it here. So we're going to draw the radius from the origin, then we're going to connect it up to the x-axis. Cool, and then we're dealing with a right angle triangle that is here. So one thing to note is that this x here is 4. So we have 4 this way. but then we have to place it because negative x is to the left and negative y is to the bottom. So they haven't told us this negative, and that's why they've cancelled out, because a negative 3 over a negative 4 is a positive ultimately. But we have a negative 4 for our x value and then a negative 3 for our y value. If it was on this side, we'd have a positive x. If it was going up this way, we would have a positive y based on our Cartesian plane. But now we have a negative 4 here and a negative 3 based on this triangle. And then what we need in order to just plug anything into sine b, because sine b equals y over r. So it means we need the r, and that is why we're doing this whole construction, is that we then have to go ahead and we have to plug this into Pythag to get our hypotenuse or our radius from the origin, which means we can ignore the negatives when we plug it into Pythag, because the negatives are ultimately going to become squared, which means they're going to disappear anyway. So we're going to have 3 squared plus 4 squared equals r squared. And then we can go ahead and we can solve for this. 3 squared is 9. Plus 4 squared is 16 equals r squared. And then 9 plus 16 is 25 equals r squared. Square root that. Therefore, r equals 5. And then our radius is always positive, whether it's going here, there, or in this quadrant 3 where we're at. So we have a positive 5 for our radius. And that means we've set this whole thing up without using a calculator. And then we can just go ahead and we can plug it into here. So our y value, because we're not trying to get the angle of the beta. We don't want that, but we do want what these sides are represented in the form of sine beta. So this is beta over here. And now we just need to take the sides that correspond with this trig function, which means if we put our negative 3, because that is our y, over our r is 5, we will then be done, and that'll be our answer for this guy. So we have our construction, we have what we're dealing with there. So that was 3.1. We just earned 3 marks there. 2 marks for the construction, 1 mark for just plugging it in correctly. And then 3.1.2, it says 2 minus sine 2 beta. So whenever something is affecting an angle here, or like this guy coming up for 3.1.3, we have to unwrap it in some sense. Whenever there's a 2 here, we have to check our formula sheet because we have a double angle formula over here. So what we need to do is we need to keep the 2 there, but then we need to expand the sine 2 beta, because we can't just sub in based off of this angle, because our reference angle is only beta, which means we have to expand it into 2 sine beta cos beta. 2 sine beta cos beta. And now we're at the stage where we can just substitute our values in, because then it means we have 2 minus 2, because the 2 stays there. Sine beta, we already calculated here. It was negative 3 over 5. And then cos beta is, as we see here, cos is x over r, which means this is our x, this is our y, remember, and this is our r, which means we have negative 4 over 5. Negative 4 over 5. And then at this stage, we can just go ahead and simplify it. So we're going to leave the 2 out here, and then we can multiply these guys. So we're going to leave the 2 there, and then top times top is minus 3 times minus 4. So at this stage, we can do it with our calculator. They said without the use of a calculator, but you can just check. But doing it mentally is also a good way of practicing. So minus 3 times negative 4 is 12. 5 times 5 is 25. So we have 12 over 25. And then this guy is 2 minus 2 times 12 is 24 over 25, because top times top, and then 1 times 25 is that. At this stage, we can just expand our 2 to have the same denominator as the 25, which means it becomes 50 over 25 minus 24 over 25, and we are left with 50 minus 24 is 26 over 25. They do not give you any marks for expanding it through all these steps. At this stage, you could just write your answer from here using your calculator, but I just wanted to show you all the steps there. But we did get a mark for expanding this guy, substituting in our correct values, and then solving for it from there. So that is 3 marks. Great. Because then we have 3.1.3, it's saying cos squared 90 minus beta. So that is a cofunction. We have to keep in mind whenever there's a 90 that we have to be on the lookout for some sort of cofunction up here. 90 minus theta places us in our all quadrant. 90 plus theta places us in a quadrant where only sine is positive, but we'll talk about that as it comes up. So what we need to do is we first need to place this. So when we do a cofunction, 90 minus it, we change it from, so cos 90 minus theta becomes sine theta. These guys work the same way. So cos 90 minus theta becomes sine theta as we place it in the all quadrant. So either way, it is positive. If we had sine 90 minus theta, it would then just become cos theta. Sine and cos are the cofunction rule. So we just need to keep in mind that if we are swapping them, 90 minus, we just change them and keep them positive. So what we need to do is we don't drop the square, but what we do is we turn it into sine squared beta. So 90 minus beta is over here, and then we turn it into sine beta. And then what we do is we keep the square, and then we go here, minus 1. And then at this stage, this is also only 3 marks, which meant it was just one move, just changing the form, and then we can just go ahead and substitute our values in. So we're going to keep the square out, we're going to keep the minus 1 here, and then what we need to do, like we had here, sine beta was negative 3 over 5. So we have minus 3 over 5, and then we can just go ahead and square both of them. We can do this in our calculator at this stage, but minus 3 squared is 9, 5 squared is 25. The negative squared was positive, so that's why I dropped that. And then we go here, minus 1, and then we can go ahead as 9 over 25 equals 25 over 25, and we are left with minus 16 over 25. Great job, guys. And that is 3 marks there. So 3.2, it says evaluate this whole thing here. So we're trying to simplify this as much as we can. So we have minus 1 plus cos 180 minus theta times sine theta minus 90 over cos negative theta times sine 90 plus theta times tan squared 540 plus theta. I'm just going to rewrite it up here so long, already placing some of the angles in the quadrants, because a reminder that what we're doing here is we have 0 degrees, we have 90 degrees, we have 180 degrees, we have 270 degrees. So we have CAST. So what we're trying to do, ignoring 270, is place these angles in the quadrants so we can drop the 180s and the 90s. If we have 180 minus theta, we are placing it in a sine quadrant, the second quadrant, where only sine is positive. If we are going 180 degrees plus theta, we are placing it in tan quadrant, where only tan is positive. This is the same thing here with our 0 plus theta or 360 plus theta. And then same as 0 minus theta or 360 minus theta places us in the quadrant where only cos is positive. So we spoke about cofunctions as well, so we'll get into that just now as well. But for now, we will deal with this first. So minus 1, I'm just going to leave as minus 1, but cos 180 minus theta. So 180 degrees minus theta places us in the sine quadrant, which means only sine is positive there, which means it becomes a negative cos theta. What we're trying to do is drop the 180, drop this whole angle here, so we can just have it in terms of theta, and we have then just placed it, and because only sine is positive in the second quadrant, it is therefore negative. And then this is timesing by sine theta minus 90. Okay, so theta minus 90 is a cofunction, almost, but it's not in our normal form of 90 minus theta or 90 plus theta. Okay, so what this means is that the best move for us would be to take a negative out so we can then swap our 90 and our theta. Because what happens is if we take a negative out, we can then go sine 90 minus theta. Because at this stage, if we were to distribute the negative back in, it would make this guy a negative 90. That is what we had here. And if we distribute this back in, it makes it a positive theta. And that is what we have there. But now we have it in a form where we can do a cofunction and turn it into cos on the next line. So we have simplified the top line somewhat, and then cos minus theta. So minus theta is dealing with this guy. So we can add a 360 if we want to, but it is the same thing as going 0 minus theta. And one thing to keep in mind is that they're like this one because we automatically think we can just take a negative out, and that is placing it. But cos minus theta is saying 0 minus theta, and that places us in our fourth quadrant, which is where cos is positive. So if we are placing it in the fourth quadrant, it means that cos is just theta here. It is a positive theta, cos theta. Okay, and then sine 90 plus theta. We'll deal with that on the next line as we deal with this guy. So I'm just going to rewrite that for now. And then tan squared 540 minus theta. So 540 is outside of our 360 degree range. What do we do when we have something outside of our 360 degree range is we subtract 360 degrees from it. Because say now 540 is somewhere around here, for example. I'm not sure where it is, but say now it's here. If we subtract 360, we do a whole rotation and we end up exactly back here. But then we're just in a range that we can work with more comfortably because then we can do some sort of reduction from 180 or 360 to place it in a quadrant. So what we need to do is just subtract 360 from here. So 540 minus 360 is tan squared. We'll leave the square there for now. 180 plus theta. So 540 was here, did a 360 rotation back, and we ended up at our 180 again. Okay, so we've simplified a little bit on each line. A reminder that this is a 7-mark question, so there's a couple moves to evaluate, which means we're going to simplify it usually to either one trig function is how they often ask it, or a very simple number like a -1, -2, +1, +2, 0, for example. So we're going to see where this is going to take us. But right now we can keep the -1 as is. We don't want to expand it into a grade 11 trig identity. Cool, and then plus and minus cos theta is minus cos theta, and then we can go ahead and deal with our cofunctions. So minus, we took the minus out just to swap this guy in the sense that we got it in a standard form, 90 minus theta, but now we keep the negative there. That is still there. We're just trying to see that when we do our cofunction, are we going to get another negative out, or is it just going to be positive? So a reminder that 90 minus theta places us in our all quadrant, which means it is positive there when we turn it into cos. So we keep the negative out, and then we go ahead and we go negative cos theta because the negative was out, but then when we did this sine 90 minus theta, it became positive. So a minus and a positive gave us a negative cos theta. So we have that over there. So then we have cos theta over here. And then sine 90 plus theta, that guy's a bit different. We haven't dealt with this yet together, but 90 plus theta. So what is important when we're doing the cofunctions of 90 plus is that we first have to see, is sine positive in this quadrant? Yes, it is. So therefore we have to take the positive out, and then we can go ahead and we can turn it into the cofunction. By that, I mean, we can just drop the 90 and go cos theta. So this guy is also just cos theta. But what happens when we go cos 90 plus theta is that is cos 90 plus theta, we are in this quadrant here, only sine is positive in this quadrant, which means we have to take a negative out first, and then we only change it. So we took the negative out because cos is negative in this quadrant, and then we go ahead and we change it into sine theta. So this guy is the only different one as far as the whole cofunction where it gets a negative. But what this means is that our sine 90 plus theta just becomes cos theta. And if you see where we're at right now, we have a cos theta times a negative cos theta, and here we have a cos theta and a cos theta. So things are becoming more similar, so we can ultimately cancel. So then what we have is tan squared 180 plus theta. So tan squared 180 degrees plus theta, 180 plus theta is over here, like this guy, 180 plus theta, which means we are in the tan quadrant. So either way, if this was negative, we would just square it and the negative would disappear. But the fact that it is in the tan quadrant, tan is positive there, so we can just drop the 180 and we can keep it as tan squared theta. We do not drop the square though. So at this stage, we can simplify some stuff, because -1 is -1, minus cos theta times negative cos theta is minus cos squared theta, and then cos theta times cos theta is cos squared theta, cool, times tan squared theta over there. And then what we can do is just distribute this negative. So negative and a negative is a positive. So we have negative cos squared theta over cos squared theta times tan squared theta. Great. So we've just earned 5 marks, which means we're not too far away. They did ask us to evaluate. And then at this stage, we need to see how can we simplify this further, because this -1 plus cos squared theta looks very similar to a manipulation of our grade 11 identity, where we have sine squared theta plus cos squared theta equals 1. And once we take something over, for example, sine squared theta equals 1 minus cos squared theta, which means this guy is +1 and a negative cos, but here we have a -1 and a positive cos. So all that means is that we can take a negative out and then we can swap the signs, and then we get it in a form that we want, because a -1 distributed back there is -1, negative cos squared theta is positive cos squared theta, and that has the same meaning. So this is looking pretty good for us, because then we can convert it into something like this. And then this cos squared theta, nothing we can do there yet, but whenever we see a tan squared theta, that's also a grade 11 identity, sine over cos equals tan, whether it is squared or whether it is just normal. So that means we have a sine squared theta over cos squared theta. Okay, so at this stage, this is looking pretty good for us, because then we can just cancel that cos squared and this cos squared, and also keep the negative out. We can convert this 1 minus cos squared theta into sine squared theta. So we have sine squared theta over there, and that is over. What is remaining is the sine squared theta over here. And this is the aim. This is what we are going for. The same thing over the same thing. thing, we keep the negative out, and we just end up with a -1 as our final answer. Great job, guys. So that just earned us 7 marks. Cool. And then final question for this section, 3.3. It says prove the identity of sine theta minus cos theta squared over 1 minus sine squared theta equals 1 over cos squared theta minus 2 tan theta. So this is 5 marks here. And what we do for an identity is we work on the left-hand side or the right-hand side. Sometimes we can work on both. We often can. But the most common setup is that we work on the left-hand side because there's usually more to do there. And then we can turn that into the right-hand side. But whatever you see, try and go for it. See where you're at. See it, that is getting closer to the other side that you're working for. Always reference the other side. Okay, so I'm going to work on the left-hand side over here, which means sine theta minus cos theta squared. Okay, so this guy is almost looking like this guy, but it's not quite the same thing. And 1 minus sine squared theta, this is the exact same as cos 2 theta. So we can see maybe there's something there that we want to do. But very often when it comes to identities, we want to factorize and expand. So there's simplifying this guy. We can probably use the SMS method to expand this whole thing. And then maybe we keep this guy. This guy also kind of looks like dots. So we have 1 minus something squared, which means that is awfully similar to dots. So it looks like dots. The last option is that this 1 minus sine squared theta looks quite similar to a manipulation of our grade 11 identity. So 1 minus sine squared theta will become cos squared theta. Okay, that looks even better for us because we have a cos squared theta here at the bottom. So that means what we want to do, we've seen our options. As we approach and take an option, we'll see if it's moving us closer or further away. And then from there, we'll start to gauge what move is the best move to move us closer to the other side. So what we have right now is we have sine theta times sine theta becomes sine squared theta. Okay, sine theta times negative cos theta is minus sine theta cos theta, but times that by 2 is minus 2 sine theta cos theta. That's pretty good for us because that looks something like this, for example. And then minus cos theta times minus cos theta is positive cos squared theta. So if we just treat sine and cos like x and y, it becomes a lot easier to see what we're working with because this is just algebra with trig functions added in the mix. And the fact that trig functions are added in the mix means we have different ways that we can factorize and change our forms in order to cancel and get what we want. So this is the whole top numerator. And then what we're trying to do, 1 minus sine squared theta, that does give us cos squared theta because of our grade 11 identity. So we have cos squared theta at the bottom. That's pretty good for us. Okay, so that guy is on track. This minus 2 tan theta, there's something going on there, but that usually means we're going to have a sine over a cos, and then we can just squish them together, and then we can simplify it. So what I'm going to do here is rearrange some things because sine squared theta plus cos squared theta, if I put them next to each other, that is exactly our grade 11 identity, and we can turn them into a 1, and that'll give us this 1 up here, which means sine squared theta plus cos squared theta. I'll rewrite them next to each other first. Minus 2 sine theta cos theta over cos squared theta. So that's looking pretty good because this guy is going to give us a 1 once we squish them together. And minus 2 sine theta cos theta, there's a 2 over there, a tan theta is here, and then we have a cos squared theta at the bottom. But we only have a cos squared theta on one side of this, which means a good move for us would be to split our base. So I'm going to turn the sine squared theta plus cos squared theta into 1. Awesome. And then I'm going to split the base where this guy gets the cos squared theta in the denominator, and then this guy gets the cos squared theta in its denominator separately, because then we can simplify things over each denominator. So sine squared theta plus cos squared theta equals 1. We have the cos squared theta over here, and then we have minus 2 sine theta cos theta over cos squared theta. This hasn't changed the meaning, it's just changed the formatting so we can simplify a little bit easier. So 1 minus cos squared theta, we have got this whole guy, so that is simplified how we want it to be. Great. And then what we can do, because this is over its own denominator, is this cos squared theta and this cos theta. This whole 2 sine theta cos theta is multiplying, which means we can start to simplify it. So we can cancel out this square there, and this whole cos theta is gone. So we're simplifying it. This was a square, that was 1, which means we have cancelled out the whole 1, and we're left with 1 cos theta at the bottom. So what that means is we have 2 sine theta over cos theta, and that is looking very good for us because this guy is solved, but minus 2 tan theta, sine theta over cos theta becomes our tan theta, which means we have 1 over cos squared theta minus 2 tan theta. And that is the right-hand side. Great. So we've got that, and then therefore we just write LHS equals RHS. And that is our final answer. So we've just earned 5 marks there and 21 marks for this whole section. Cool, guys. So we're on question 4 now. So 4.1, it says given cos A minus B equals cos A cos B plus sine A sine B. 4.1.1, use the above identity to deduce that sine A plus B equals sine A cos B plus cos A sine B. So this is 3 marks. They love this question. I've seen it in every June paper, every prelim, every final, some sort of proof with a compound angle. So what we need to do is we need to do a cofunction here for the original thing we're working with. As we do a cofunction, we're then going to substitute everything into this side, and it's going to end up turning into a sine A cos B plus cos A sine B. So I'm going to do that here. So we have cos 90 minus A minus B, because A minus B was our initial angle. So it's like saying 90 minus our initial angle, theta, for example. Once we have this, we can turn it into a sine. So that has given us this portion of it. Then from there, what we're doing is we're distributing this negative into both of these angles. So we're just trying to unpackage that whole angle so we can then repackage it. So what I mean by that is 90 minus A, we have times the negative in there, and then negative times negative B is positive B. At this stage, what we have is we can just repackage this guy as our first angle, 90 minus A plus B. So we have the A portion, we have the B portion, we've turned it into sine, and now we have to go ahead and substitute this into this original guy on the right side. So what that means is cos, wherever the A used to live, we have to go cos 90 minus A. Because A used to live there, but now we are repackaging the cofunction where A now lives. So cos 90 minus A, this B we're just going to distribute normally, so it means we have cos B over here. And then what we have is plus sine A is what used to live here, but now we have to redistribute this 90 minus A into here, which means we have sine 90 minus A, and that is multiplied by this B we're just distributing normally into sine B. So to retrace our steps, we did a cofunction of our initial reference angle. We then distributed the negative into both, and we repackaged the 90 minus A here as our first angle and distributed that into this whole compound angle on the right. Because now we're just one move away from having this whole sine A cos B, cos A sine B, because we have a cofunction, which means we are 90 minus theta, placing us in the all quadrant, which means we can just turn this guy into a positive sine A. This guy stays cos B, okay, and that is what we have here, sine A cos B, and then our plus stays out there, sine 90 minus A becomes cos A. Cos A is what we want. Great. Times sine B stays the same. And through that move of changing it into a cofunction and distributing it throughout the original, we have then turned this whole thing into a sine A plus B on the left side, because we dropped this angle, 90 minus A is sine A plus B. So we have that over here, and then we distributed the 90 minus into this whole right side to get the same compound angle on the right. And that has earned us 3 marks. Great job. Okay, so then 4.1.2, it says hence or otherwise determine the general solution of this equation. Okay, so we have sine bracket 2x plus 50 bracket minus sine 15 cos 48. These guys are multiplied together equals sine 48 cos 15. So whenever they say hence, it means, okay, probably look at the question before, because sine A cos B, cos A sine B. We have a sine, we have a cos, we have a sine, we have a cos. So it is very similar to this guy. It's just in a different format. So we'll just repackage it. But in order to do a general solution, what we need to do is take the sine 15 to this side. So a general solution, we would look if we had the same trig functions, and then we would try and divide by them, or we would see how we could factorize. But in this stage, whenever there's something affecting the angle in this guy, for example, we have a compound angle, and the best bet is to take this over to this side so we can then see what we need to do. The hence, once again, told us to work with some sort of compound angle, and these angles here are very specific. So what we have is sine 2x plus 50 over there, and that equals sine 48 48 cos 15 plus sine 15 cos 48. Or I can swap them saying cos 48 times by sine 15. So sine 48 cos 15 cos 48 sine 15. These guys are multiplying, so it doesn't matter that I changed the order of them, but that gets us closer to a compound angle. Because right now we have sine 2x plus 50. This will stay here. So we have sine 2x plus 50, and this equals sine angle, cos angle, sine angle. So a sine and a cos plus a cos and a sine is the same as this one that we just calculated here, which means it turns into, when we repackage it, into sine a plus b, which means we have sine 48, because this is the compound angle we are working with, sine 48 plus 15 in brackets. So we have repackaged it. We have a sine here, we have a sine here. We can just go ahead and we can simplify inside this bracket because these are just numbers. So that means we have sine 2x plus 50 over here. This equals our sine 63. At this stage, we're good to go. So we can divide by sine on both sides. So we cancel sine and we cancel sine, but we do not try and solve for the x individually, because at this stage, according to our cast diagram, this guy here was our reference angle, which meant it was a positive sign here. Otherwise, we would have had a negative here if we took something over. So sine is positive. So that means we're dealing with quadrant 2 and quadrant 1. So at this stage, we're going to bring both of these guys down into quadrant 1 and quadrant 2. So here we have a Q1. This whole angle here represents our theta, and this whole angle here is our reference angle. So usually we'd go something like theta equals x plus k 360. K is an element of z. But at this stage, what we need to do is we need to bring this 2x plus 50 down to the theta here, and this 63 down to the side as we place it in each quadrant. So that means we've divided by sine, we've figured out which quadrants we're in, and then we're going to go ahead and we're going to bring the 2x plus 50 down here because that is our angle. Then from there we have 63 because we're in quadrant 1. We don't have to go any reduction because 0 plus 63 is still 63. For quadrant 2, we're going to do the 180 minus this reference angle. For this guy, we have 63 plus k 360 because sine has a period of 360. So does cos, tan has a period of 180. And then for 1 mark, we always just have to write k is an element of z somewhere, because then we can go ahead and we can solve for this. So we're going to keep the 2x here. We're going to take the 50 over, which means we have 63 minus 50 is 13 plus k 360. K is an element of z. Divide by 2, and we have to divide this guy by 2 and this guy by 2. And that's why we don't try and solve for the angle up here, because otherwise we might not do a reduction of the period. So 2x divided by 2 is x. 13 divided by 2 is 6.5 plus k 180. K is an element of z. And then this was quadrant 1, which just means we're in quadrant 2 over here. And then quadrant 2 is very similar. We bring down our angle. So we say 2x plus 50, and that equals, only one thing to keep in mind here is that we have to place it. This was our reference angle, which means we have to go 180 degrees minus our reference angle to place us in quadrant 2. So we have 180 minus 63, because that was our reference angle up here, plus k 360. K is an element of z. Once again, we have to write that for 1 mark, and then we can go ahead and we can simplify. So we're going to leave the 2x here, 180 minus 63 minus 50, simplify that on the next line, plus k 360 over here. K is an element of z. And then what we have, 180 minus 63 minus 50 is 67 degrees. So 2x equals 67 plus k 360. Cool. And then we have to divide everything by 2. So x equals 67 divided by 2 is 33.5. And then k 360 divided by 2 is plus k 180 degrees. And then these are our angles that satisfy this general solution, 33.5 plus k 180 in quadrant 2 and 6.5 plus k 180 in quadrant 1. And that just earned us 4 marks for this general solution. So question 4.2, it says if cos x plus 30 equals negative 2 sine x, deduce that tan x equals negative 1 over the square root of 3. This is a 5-mark question. The general theme that we've had so far has been a lot to do with our compound angles, not our double angles here, our compound angles. So the fact that we have a cos x plus 30 equals negative 2 sine x, this negative 2 sine x isn't like this guy. It's not sine 2 theta, and it's not necessarily anything up here just yet. So we can maybe have a look at that, but these guys aren't similar either. So the only move that we can really start off with in order to get the tan x equals negative 1 over square root of 3 is expanding our cos x plus 30. Okay, so cos x plus an angle becomes cos A, cos B minus sine A, sine B. So if we go ahead and we expand it here, we have cos x times cos 30 minus sine x times sine 30. And then this equals minus 2 sine x. So next move here is the fact that we have a cos 30 and a sine 30 means we have our special angles. These guys, we can either do our Nova table or our protractor, whatever method we use, or we use our calculator because they didn't specify that we can't use our calculator. So that means we can simplify the cos 30 and the sine 30. So cos 30 is the square root of 3 over 2. And this is multiplied by cos x over here. And then minus sine 30 is 1 over 2 times sine x. And that equals minus 2 sine x. So at this stage, these guys are both over a 2, which means we can multiply by 2. So we can drop the denominator. It'll make it a bit neater for us, which means we have the square root of 3 cos x minus sine x, because both of these guys had the 2 in the denominator, which meant we just dropped them. But what we did have to do, and what we are doing, is multiplying this guy by 2, because it was only over 1. So we have to multiply it by 2, which means we have minus 4 sine x. So at this stage, it's a lot neater. A reminder that we're going for a tan x equals minus 1 over the square root of 3. So we've done some good work so far. So what we can do now is take our negative sine x over here, which means if we take it over, it becomes a positive, which means we're left with minus 3 sine x over there. What is remaining on our left side is the square root of 3 cos x, because we took this guy over, which means we're not far from a tan. A tan x is just sine over cos, which means we can move our cos down here. So we're going to keep the sine x over here. We can move the cos x down there. So we're dividing by the cos x. And then what we can do is we left our square root of 3 up here. So this guy stayed. And then we can divide by our negative 3 here. So what we have is dividing by negative 3 over there. And then at this stage, what we're going for is a square root of 3 at the bottom and a 1 at the top. So we're closer. This guy is just tan by itself. So sine x over cos x is our tan x. That's great. That's what we wanted. And then I'm just going to move the negative out in front here. So let's call that guy positive and just put the negative here, because we can either have the negative here or in front or at the top. It doesn't change the meaning as long as we only have one negative in this case. So we have minus square root of 3 over 3. And then what we need to do in order to get a square root of 3 at the bottom is we have to times by a reciprocal. So what that means is that we're timesing by 1. But if we times by square root of 3 over the square root of 3, we haven't changed the meaning, but we have then made it easier for us to get it in this form where we have negative 1 over the square root of 3. We already have the negative here. So now we just need to go ahead and simplify this by timesing top and top and bottom, which means we have minus square root of 3 times the square root of 3 just becomes 3. It's like squaring a square root. And then what we have at the bottom is we have 3 times square root of 3 means we have 3 surd 3. And this equals tan x over here. And then we're just one move away because we can just cancel the 3 and the 3, means we're left with tan x equals minus 1 over the square root of 3. And that is what we wanted over here. If cos x plus 30 equals negative 2 sine x, deduce that tan x equals this value minus 1 over the square root of 3. And we have that over here. So we're on question 4.3. It says, given the expression 4 sine x cos x divided by 2 sine squared x minus 1. 4.3.1, simplify the above expression to a single trigonometric ratio. So what we have here is a 4 sine x cos x. This guy looks very similar to this guy over here, this 2 sine x cos x. But what is different is that this guy has a 4 and that guy has a 2, which means we can just go ahead and we can change the formatting, but not the meaning, saying 2 times 2 because that equals 4. And then we just keep our sine x over here times by cos x over there. And then what we have at the bottom is 2 sine squared x minus 1. This looks very similar to 1 minus 2 sine squared x. So this guy, all we need to do is take a negative out and then we can swap the order of this and this, and then we can have it in that form and we can turn it back into a cos 2x. So we're going to take the negative out. We have a negative and then it becomes minus 2 sine squared x plus 1. Okay. And then at this stage, what we can do is this 2, we can keep it out there, but 2 sine x cos x, we can convert into sine 2x. So we can condense this double angle and turn it into a sine 2x. At this stage, we had the negative out there, but we can swap the order saying 1 minus 2 sine squared x. So 1 minus 2 sine squared x, as we spoke about, is just turning into a cos 2x. And this is great for us because we have a 2 over there, we have sine 2x over here, and then we keep the minus out and 1 minus 2 sine squared x becomes cos 2x, which means we're just one one move away from simplifying the above expression to a single trig ratio. And then we're going to put the negative at the top. We're going to keep our 2 there because the positive times the negative is negative. 2 is over there. And then sine 2x over cos 2x just becomes tan 2x. And that is our final answer, having converted the above expression to a single trig ratio. So then 4.3.2, it is saying for which values of x in the interval minus 90 to 90, so x is between that range, will the above expression be undefined? Okay, so this is 3 marks as well. So what we need to do is whenever they're talking about undefined, we need to look at the denominator, because if we divide by 0, anything divided by 0 equals undefined. So we're just going to take this denominator and make it equal 0. So we have 2 sine squared x minus 1 equals 0. Then we can go ahead and take the 1 over. So we have 1 there. We have 2 sine squared x over here. We can then go ahead and we can divide by 2, bring the 2 down here. So we have sine squared x equals a half. And then what we have left is square rooting this guy and square rooting this guy. And whenever we square root an x, we get a positive or a negative outside. So we have the square root of 1 over 2, positive or negative, and that equals our sine x over here. So at this stage, what we need is the value for x in terms of angles. Right now, we just have the lengths of the sides. We're going to have to shift sine negative square root a half and shift sine positive square root a half, and then we can get our 2 angles in this range. So if we divide by sine over here and we shift it on our calculator, we're left with the angle of 45 over there with the positive square root of a half, and x equals minus 45 for the negative square root of a half, which means that is our final answer because we are within the range of minus 90 and 90. Both of these angles fall within there. And if we do any rotations adding 360, because that is the period of a sine graph, it'll take us outside of this range. So if we add 360 or subtract 360 from 45 over here, or same thing with our negative 45, it will take us outside of this range, which means these are our final answers over here. And then question 4.3.3, the final question of this section, it says without using a calculator, determine the value of 4 sine 15 cos 15 2 sine squared 15 minus 1. So it's only 2 marks, and this is a follow-on question, just like they've all been. We simplified to a single trig ratio, we got the undefined portion, and now we are here. So this thing looks a bit messy for us, but a reminder that in our previous question, we calculated and proved that this expression here, this 4 sine x cos x, we have 4 sine 15 cos 15, same formatting, just with actual angles there. 2 sine squared x minus 1, we have 2 sine squared 15 minus 1, which means we simplified this whole expression to a single trig ratio, and we made that equal, and this was the correct answer, minus 2 tan 2x, which means we don't have to try and solve for this whole thing again. What we can just do, we can plug the angle of 15 into x over here, and then we can solve for it without a calculator, because then what we have is minus 2, tan is over here, and then what we have is 2 is the angle inside there, times by 15, because x is the angle we're working with. X is 15 in this case. If we were to rework the whole thing and get to the same expression, which means we can just go ahead, we can multiply inside the brackets. So we have minus 2 tan 2 times 15 is 30. 30 is great for us. It's saying without the use of a calculator, which means we either have to use our Noah table or our protractor in quadrant 1 to get that angle. So we have minus 2 tan 30. If we were to use our calculator, we could get it, but let's do it. Minus 2 tan 30. So I'm just going to quickly draw the protractor here for these special angles. So we have this guy. This is the first quadrant of our Cartesian plane. So that means we have a 90 over here. We have a 0 degrees here. We have 3 other angles over here. This guy is 60. This guy is 45. And this guy is 30. Just a reminder, we're just making a protractor in the first quadrant here of our Cartesian plane, which means if this is our y-axis there, and that is our x-axis, when we are directly on our y-axis, we have an x value of 0. So we have the square root of 0. And then here, we just need to know this starting point. It is the square root of 4 is the y value. That is x and that is y. So as we move this way, all we need to do is we need to move this guy up by 1 unit. So we have the square root of 1. It was 0, but now our x is the square root of 1. And the square root of 4, we have to move down by 1 unit, which means we have the square root of 3 over here. And this just repeats. This x value moves up 1, so we have the square root of 2. This y value moves down 1, so we have the square root of 2 here as well. Then over here at 30 degrees, this guy was 2, so it becomes the square root of 3. And this guy here moves down 1, getting the square root of 1. A reminder that these are all x's and y's. So these are coordinates on a curved plane. And then our last thing here for 0 is the inverse of this guy, but we can just continue with the trend that this guy was 3, so it becomes the square root root of 4, and this guy, the y value, becomes the square root of 0. So now we have our special angles based on x's and y's throughout, and then the only other thing is that r equals 2 for all of them. If we were to draw a radius there, a radius there, a radius there, or there, it is the same length, it equals 2, which means at this stage, tan of 30, tan is y over x, tan is tix or o over a, which means we have to go to the 30, the angle over here for 30. We have to take the y, which is the square root of 1, and put it over the x, which is the square root of 3. So that means we are just substituting the whole thing, tan 30, we are replacing it with the square root of 1, which is just 1, because that was our y for tix, over the x value, which is the square root of 3, which means our final answer is minus 2 times 1 is negative 2 over the square root of 3. And that is how we would solve this without using a calculator, determining the value of this whole messy thing. Remembering that it was the simplified single trig ratio, and then just using our protractor or our node table to get the value of tan 30 if we weren't going to use our calculator to then solve for this. So that was 4.3.3. That earned us 2 marks and 20 marks for this whole section. Great. So we're on question 5. Question 5 is saying in the diagram below, the graphs of f of x equals cos x plus m and g of x equals sine bracket x plus n are drawn on the same set of axes for x is an element of negative 240 to 240. So we have our g graph here. Our g graph is a sine graph, and our f graph here is a cos graph. So a is the x-intercept of f and has coordinates of 60 and 0. B is the turning point of g up here and has coordinates of 60 and 1. So question 5.1, determine the values of m and n. This is a 2-mark question, which means we can just interpret our m and our n over here. So a reminder that the easiest way to interpret most of the graphs is by covering up this whole negative portion here and knowing our standard forms. I'll erase that now. But once we can compare things to the origin in the positive side, it makes it a lot easier for us to understand what graph we're dealing with and what shift has occurred. As far as the m here, the q, the shift in the y-intercept, as well as the n, the horizontal shift. So off the bat, we have our sine graph over here. Our standard form is something like this. We have one crest, we have one trough. Here is positive 1 and here is negative 1. This is 90, that is 180. We have 270 there at negative 1, and then we have 360 degrees is the usual form for a sine graph, which means we have 1 equals a sine b x plus p plus q. A reminder that a is the amplitude, which means in this case for our standard form we have a positive 1 that takes us up to a positive 1. If it was a positive 2, for example, it would take us all the way up to a positive 2. If it was a negative 1, it would then take us down first, going to a negative 1 first at the 90 and then going up like that and repeating. So our standard form is positive 1 over there for our amplitude. Our b is what affects our period. So the usual period for a sine graph is 360, cos is also 360, and tan is 180 degrees, as we'll see in another video, but a period of 360. So if our b value is 1, then it means our period fits in 360. If our b value here, for example, is 2, then we'll end up having something like this, where we have a crest and a trough going up to our 1 at 90, then down to our negative 1, and then back at 180. It'll half our period if it was a 2. And then what we have here for a positive p, this guy shifts our starting point from the origin to the left or to the right, which means if this is a plus 90, for example, it is going to shift us 90 units to the left. So that means if we had a negative 90 here, it would be starting over here, and then we'd meet the y-axis at 1, and then we'd go down to 90 and then repeat. So if it is a positive value here, it shifts us to the left. If it is a negative value, it shifts us to the right. And then the last thing, just like our functions in paper 1, a positive q just shifts up our starting point. So if it is plus 1, for example, we'd start at positive 1, go up to positive 2, come back down here, and then meet our 0 there. And then at 360, we'd be back at 1. And it would shift the whole graph up by 1 unit. So we have our standard form for a sine graph, and then our standard form here for a cos graph is very similar, which we're just going to draw now, just so we can compare our sine graph and our cos graph to the different variations we have here. So cos will start here, go down, and then back up. which means we have 1 over here, minus 1 over here, and then it intercepts at 90, 180 is here, 270 is there, and then 360 is here, back at 1, which means we have half a crest, a full trough, and then the other half of the crest over here. Okay, and this would be our standard form for a cos graph. We have y equals a cos b x plus p plus q. So the reason I just wrote out all the letters, the a, the b, the p, and the q, was so that we can see what place is being taken up in this f of x here and this g of x here, because they haven't manipulated or changed all of the letters that we can, like the period, for example, or the amplitude, but they have, in this case, for m, affected the y-intercept. Okay, which means if we are looking at our m value, we can just interpret it. Our cos graph usually starts at a positive 1, but this cos graph, this f of x, that is just cos x plus m. So that means we would usually be intercepting at positive 1, and we are now only intercepting at 0.5 for our f of x graph. It means the only way that we could make this work, based on the fact that we've only affected the y-intercept, is by making the m minus a half, because it used to start here, but now it is starting at positive a half, which means we shifted it down half a unit, and we end up with 0.5 at the y-intercept being the starting point for our f of x graph, our cos graph. So then we are moving on to n. N is shifting us in our horizontal for our sine graph. So our sine graph is our g of x over here. Our sine graph usually starts at 0 and then ends at 360. Okay, but this sine graph here, which is our g, is not starting at 0. So the best way, once again, remember we try to cover this all up, because it's kind of confusing to interpret things in the negative, because that is not where we have interpreted our standard forms. The easiest way to then interpret our sine graph is trying to find a point that we can shift in order to get us back to 0. So this number here, this negative 30, is a point that is directly on the 0 in terms of y. But if we were to shift this 30 degrees to the right, we would then have a graph that is going up like this and then going down like that, for example, which is the closest move that we can make in order to shift our sine graph back to the 0, back to the origin, to our standard form, which means if this graph has actually just been shifted 30 degrees to the left, it means our n value is positive 30, because a shift to the left is a positive. This p always works backwards. Once again, like we were talking about, if we are shifting it to the left, it is a positive value. If we are shifting it to the right, it is a negative value, which means our m is negative a half and our n equals 30. So we've just earned 2 marks over there. And then 5.2, it says write down the amplitude of f. So our f graph is our cos graph, cos x minus a half. Okay, so we need the amplitude. We can either go half bracket max minus min if we like that method, and then we can solve for it from there, or we can just go ahead and interpret our standard form, because there isn't any number or sign in front of our cos x. So we just have a cos x minus 1 over 2. This is the graph that we're looking at. This is f of x, which means there's no 2 or 3 or 4 or anything there. There's also no negative in front here, which means our amplitude for this guy, if we just interpret it, the only change that has occurred is that we have shifted the y-intercept, which means our amplitude is just positive 1, because they haven't put any symbols here or any values or signs in front of our cos x, which just means that it is a positive 1, and that is our amplitude. So now we're on question 5.3. It says if h of x equals g2 of x, write down the period of h. Okay, so here's our g graph, and they are saying h of x. So h is the new graph that we are turning this guy into. What they are doing is they are adding a 2 to our x, and the way that we would usually add that is in front of the x and the shift, which means that if we want the period of our h, this number here is now affecting our period, this 2. A reminder that our period is usually 360 degrees when our number for b is 1, but now we have a 2 here, which means for our period we have to go 360, which is the usual period for a sine graph, divided by 2, this value they added here that affects the period, which means that our period then equals 180 degrees, which means this graph is going to occur in double the time, and we're going to get a crest and a trough in 180 degrees instead of in 360 degrees. So that has just earned us 1 more mark there. And then question 5.4, it says for which values of x will f of x times g of x be less than or equal to 0 in the interval x is an element of 0 to 205. 40 degrees. So f of x times g of x is negative. That means one of these guys needs to be positive and negative, or this guy has to be negative and this guy has to be positive, because a positive and a negative going both ways will ultimately make this guy negative. You can't have a negative and a negative or a positive and a positive, because that will not satisfy this equation considering they are multiplying. So that means we have to see where is the one negative or the other is positive. So as we're moving here, 0 to 60, they're both positive in this range. But then after this point, our f of x is negative from 60 up until 150 over here. This guy is negative there, and this guy, g of x, is positive for that range, which means we have a positive all the way from 60 to 150, and this guy being negative from 60 to 150, meaning that a positive and a negative will ultimately give us a negative. So we know this part satisfies our equation, and then we also just need to see as soon as this guy crosses, it means we have a negative, and those two guys will ultimately become positive when they multiply, which means the only part that can satisfy this equation, or what they're asking, is 60 to 180. So therefore we have to write x is an element. We just need to see, are we included? We will include these different values because we are including 0, because exactly at 60 is 0 here, and 0 times anything is 0. Same thing here at 150, 0 times anything is also 0. So we're going to use square brackets instead of round brackets. In our domain, x is an element of included 60 to 150, and then square brackets here, and that is done. Okay, great. Question 5.5, it says describe the transformations that the graph of g has to undergo to form the graph of p, where p of x equals negative cos x. So this is also 2 marks. So where the graph of g now undergoing some changes to form p of x, and p of x equals negative cos x. So our g of x was this guy over here. So the fact that we need to turn it into a cos means that we are going to have to do some sort of co-function. So I'm just going to rewrite our g of x over here. So in order to do a co-function, we can go one of 2 ways. We can either try and get 90 minus, but that'll take quite a bit of work. So it might be easier to get 90 plus. So what that means is that if we shift this graph 60 units more to the left, we'll end up starting it at negative 90, which means this guy in our bracket will become positive 90. So if we turn this into sine x plus 30 plus 60, we have shifted it 60 degrees more to the left, we then end up with sine 90 plus x. So 30 plus 60 is 90, and I just moved it in front so we could get our standard form for a co-function, which means we then have a 90 plus x. A reminder that for sine 90 plus x, we are positive in our sine quadrant. So sine is already positive there, which means we just take a positive out, and then we can drop our 90 and turn it into cos x. So at this stage, we have a positive cos x, and then it needs to become a negative cos x, which means we'll just have to divide it by a negative 1, and then we end up with a negative cos x. Okay, and all that means in terms of describing the transformation, because this was just showing us the steps as to how we got to this p of x, what we did is we shifted the graph 60 units to the right. So that was over here, and then we did a reflection over the x-axis. So one mark was to describe this portion, and then the other mark is to say when we divided by negative 1, that means we just reflected it over the x-axis. And these would be the 2 marks to describe the transformation that the graph of g has to undergo to form the graph of p, where px equals negative cos x. And we just earned those 2 marks and completed this section, earning us 8 marks. Cool. Question 6 is a trig in triangles question, and we have our formulas up here. This is our sine rule, our cos rule, and our area rule. So in the diagram below, ABD is a horizontal plane and BC is a vertical plane. The angle of elevation from A to the top of the pole is equal to x. So we have x here is the angle. It is given that ADB equals 2x over here. CBD is 90 degrees and AD equals BD over there. So right now for 6 marks, there's only one question in this section. It says prove AD over here equals H, so H is over here, over 2 sine x tan x. So we need to get the H from here into this triangle here. Okay, this is 6 marks. We also have a tan x over here, which means we'll need to get a cos somewhere, either through our cos rule or through a cofunction. That is very common in this type of question. So 6 marks means what we have to do in order to get the h into this triangle is to get the common side. So we first have to get AB in triangle ABC over here. And then once we have AB, then we can work in triangle ADB over here to then get AD in terms of all of this. So the best bet is to usually start with the sine rule. There's nothing up here to talk about the area rule, so we'd ignore that. And we generally avoid the cos rule unless we have to. So if we can use the sine rule, we're going to start with that and see if we can get AB. So I'm just going to go ahead and write down the formula. A reminder that we only need 2 sides over here. In the actual formula, they've written all 3, but we only need 2 sides to work with the equation. So at this stage, the little a is to do with the length here. The sine A is taking the angle. So for this one over here, for BC, we have h, and we can plug that in as our actual length of this side. And then we are dealing with the sine rule, so we just have to put sine of x opposite the side, or the side opposite the angle, which means we have sine x over here. And then that means we want AB. So we're going for AB, but then sine B, the angle opposite AB is this angle over here. It's angle C or ACB over here, but we don't have that yet. But if we do interior angles of a triangle, we have 90 degrees here plus x plus this angle will equal 180. So if we do it up here, we have 90 plus x plus angle C equals 180 degrees. We don't need to write any reasons here. This is just interior angles of a triangle, but then we can just isolate for the C here by taking the 90 over. 180 minus 90 is 90, and then plus x, taking it over, becomes minus x over here. And this is a good thing for us because we are going for a tan x, which means we would need a cos x, and right now this has something to do with a cofunction. So if we plug it in here and we know this angle now is 90 degrees minus x, which we just solved, we can go sine brackets 90 minus x over here. So at this stage, what we want to do is we're still trying to get AB. That was the goal here. So we can just isolate for AB. But one thing before we do that, sine 90 minus x is a cofunction as mentioned, which means 90 minus an angle, theta, or x in this case, is in the all quadrant, which means everything is positive here, which means sine 90 minus x is going to turn into cos of x. So cofunction, brought it down, dropped the 90, changed the sine to the cos. And then we still had this over here. This is staying the same, but then at this stage, in order to isolate for AB over here, we can just move our cos x up here, which means we have h cos x over sine x. And then one more move, because we have isolated for AB, but sine over cos, as we know, is tan x. But cos over sine equals 1 over tan x, which means we can just simplify the cos x over the sine x and turn that into tan x at the bottom, which is even better for us because now we have the tan x that we can bring into our final answer when we solve for AD. Great. So what we want to do at this stage is solve for AD in triangle ADB. So that means we need AD. Once again, we're going to try the sine rule first before we check out the cos rule. And once again, there was nothing to do with area, so we'll just ignore that one. So what we're going to do is we're going to set up our sine rule. We want AD, so we need AD over sine of B over there, over the opposite angle of that side, okay? And we're not necessarily going to use DB because that isn't what we calculated. We calculated AB for a reason. So AB over here is what we're going to plug in, this guy, and that is over our sine of 2x over here. So AB over the sine of 2x, which means I'm just going to plug in h over tan x, our AB, in here so long, which means we have h tan x times sine 2x over here, and then AD over sine B. So one thing we have to keep in mind, we've used everything up here. We've dealt with this 2x here. We dealt with the fact that this was 90, and now we have to use this aspect that AD equals BD, because what is important here, once again, like when we calculated angle C over here, is that we have interior angles of a triangle, and this specific triangle is an isosceles triangle. So AD equals DB, which means this angle over here will equal that angle over there. So we can set that up so we can then solve for angle B over here, and then we can plug our sine B, that angle, into this equation, and then we can go ahead and we can solve for AD, and then we will get this answer. So that means if we're dealing with interior angles of an isosceles triangle, we have angle A, let's call it that, equals B equals Y. for example. They don't necessarily equal x, but they do equal the same, which means we have 2y plus 2x equals 180 degrees. Because this was 2x, we're going to call that y and this y, and all of them add up together to give us 180 degrees, which means at this stage, what we can do to get this y, this angle of b by itself in terms of x, is we can take a 2 out, which means we have y plus x over there, and then 180 over here. Divide this by 2. 180 divided by 2 is 90, and we're left with y plus x. And then once again, to isolate for y, we take the x over, and we have 90 minus x over there, which means b's angle and a's angle are both 90 minus x, which means over here, the sine b, the angle that we're dealing with opposite our AD, is 90 minus x, which we can plug in now. And once again, that'll be a co-function, just like the previous question. So over here, we have AD over sine 90 minus x, and this equals h tan x times sine 2x. So I'm just going to go ahead and turn this into cos x over there. So we have AD over cos x, because this was a co-function, and then h is over here. We have tan x. We want the tan x at the bottom, so we're going to keep that there, times sine 2x. So one thing to keep in mind is that we always have this to reference in order to know what we need to solve. So AD here is AD here, so that is good. This guy doesn't have a cos x at the bottom, which means we're going to have to move it up top. We already have an h at the top, which is great for us, and then over a tan x, which we have, and then this guy is 2 sine x. It is not sine 2x, but one thing we do know about sine 2x is that it is a double angle, which means we can expand it. So over here, I'm going to move the cos x up top. So we have h cos x, tan x can stay there, but then a reminder that sine 2x is a double angle, which means we can unwrap it and it can become 2 sine x cos x. And that is great for us because we are only one move away from having this answer. All we need to do is cancel this cos x and this cos x, and we're left with the final answer. So I'm just going to rearrange it in the form that they have with the 2 sine x first, but here is the 2 sine x that we have remaining. This was h that was remaining at top. We had 2 sine x times tan x, and that is what they wanted. That is our final answer, h over 2 sine x tan x, and we have that AD equals h over 2 sine x tan x. So question 7 is the beginning of Euclidean geometry. It builds up from question 7 being just identifying the angle, giving a reason, 1 mark for the angle, 1 mark for the reason, like then it moves to similarity, and then it moves to riders, and then we are done. This is the same format for June, prelims and finals. So question 7.1, P, Q, R, S, T lie on the circle with center O. So we have the origin, which means we have radii, and we have a diameter, for example. So these are things to keep in mind. Whenever we have a center, we have to look for radii and diameters. So PR is perpendicular to OQ. Okay, so we have the 90 degrees here, and these two lines intersect at F. Great, so we have to keep this in mind. If we have a 90 here, we also have a reason that we can work with. So POT is a straight line, so that means that is our diameter, and then P1 equals 42 degrees, which they gave us on the diagram. So 7.1.1, determine giving reasons the sizes of each of the following angles. So R1, what is very important here is that POT is a straight line and that O is the center, which means PT is a diameter, and this shape here is a right angled triangle because we have angle in a semicircle. R1 equals 90 degrees. We got 1 mark just for saying that. If we didn't know the reason, we could still write this and we'd get 1 mark. And then all we write is angle in semicircle. So now that we have that, these questions lead on. This was A, and now we're on B. They want the angle of S. So S is over here. So we need to see, are we going to work from this 90 degrees here to get S, or are we going to work from this P1 where they gave us the angle 42 over here? So getting from 90 into there is a bit tricky, which means going from the 42 degrees, jumping directly opposite, because then we are in PRST, which means this angle, S over here, is the opposite angle of P1. And a reminder that if all 4 points are touching the sides of the circle, it means we're dealing with up angles of a cyclic quad. So that means we don't have to write all our working out, but we can just do it just so we can understand. P1 plus RST over here equals 180 degrees. We don't get a mark for showing our working. This is up angles cyclic quad. And then at this stage, we know P1 is 42 degrees plus RST is there. That equals 180. We take the 42 over and we are left with RST, and RST has a value of 138 degrees. So P1 plus S add up to 180 degrees because up angles cyclic quad. And now we're on C, a follow-on question asking us for the angle of PQR. So PQR, this whole angle here, Q1 and Q2 together. So there's a couple ways that we can do this. There are multiple different shapes here. We have triangles, we have various cyclic quadrilaterals, and then the question we ask ourselves is, can we use this 138 degrees to calculate Q1 and Q2? I imagine we can, but it's a bit tricky at this stage. The easiest way might be to work with this 90 degrees here, this R1, because if we work back in triangle PRT, we can then calculate T2 here. Once we have T2 here, we can then work in this cyclic quadrilateral QRT. And then once again, T2 plus Q1 and 2 combined add up to 180 degrees because opposite angles of a cyclic quadrilateral. So we're working in two different shapes. We have the triangle, which we're going to get T2, and then we're going to work in this other quadrilateral to get Q1 and Q2. So it's 3 marks, which means we get 2 marks for a statement and 1 mark for a reason. Okay, so T2 equals 180 degrees minus 90 minus 42. So we don't have to show our working. We can just do it on a calculator. And this equals 48 degrees. Great. So this is interior angles of a triangle. And now, like we spoke about, T2 plus Q1 and Q2 equals 180 degrees because of up angles cyclic quad, which means we just worked out T2. It is 48 degrees. So we have 48 degrees plus this guy equals 180 degrees. Take the 48 over, and PQR, like they were asking for here, equals 132 degrees. Okay, great. So 7.1.2, it is a 3-mark question. It says if PR, so PR over there is 7 centimeters and QR over here is 4 centimeters. I'll mark that down. So we have 4 centimeters. Determine the length of QF. Okay, so QF is over here. That is a question mark. That is what we want, this length over here. So once again, this is 3 marks. What we're dealing with at this stage are the lengths of a triangle, QFR, because once we are in QFR, we can then use Pythag to calculate QF. So they've given us QR, that is 4 centimeters here, and then FR we can calculate from the fact that we know PR equals 7 centimeters. So PR equals 7 centimeters. This is given. We don't get any marks for that. But then PF equals RF equals 3.5 centimeters because line from center perp chord. So we see that this line from the center, this radius, is perpendicular to this chord here, PR. And this is one of our reasons, which means that this length equals that length. And therefore, if this whole thing was 7, it means PF equals 3.5 and RF equals 3.5 centimeters as well. So now that we know that FR is 3.5, we also need to get a 90 degrees in triangle QFR. And that is quite easy for us considering they've already given us this 90 degrees here, which means QFR, the angle for it, equals 90 degrees as well, because we are doing angles on a straight line. So we have angles on straight line. And now we're in triangle QFR. We have the 90 degrees. We have the lengths of 2 sides, which means we can just go ahead and do Pythag in order to get QF here. So QF squared equals our 4 centimeters squared minus our other side, FR, our 3.5 squared. Okay, so we have Pythag over there. Cool. And then we can just go ahead and solve for this in our calculator, squaring these guys, subtracting them, taking the square root. So we have 16 minus 12.25. That equals 3.75. And then we just need to take the square root of that. And we have QF equaling 1.94 centimeters. And that is our final answer. Great. And then question 7.2, in the diagram below, B, D, and C lie on the circle with center O over here. AB over there and AD are tangents to the circle at B and D respectively. And then they have BAD is 59 degrees that they're marked on here. So we're working with tangents. We do have a center of a circle, so we can keep that in mind. So determine, giving reasons, the sizes of each of the following angles. We are calculating B1 over there. So 4 marks. B1 over there, and the only angle they've given us to start with is angle A over here. So one thing to keep in mind, whenever we have a tangent, we're looking for tans from the same point. That is very important, which means the fact that B is over here and D is over there, it means that AD is the same length as AB. That'll be great for us. One other thing to keep in mind is tan chord theorem, should we need to get into the circle. And then if there was exterior angle of a cyclic quad, we'd look for that as well. So that means we're at a good starting point. The fact that we want B1 is great, considering we know the angle A and we know AB is AD. We do have to write that with a reason. So we're going to start there. AB equals AD tans from same point. So because of that, we can then do interior angles of a triangle, saying A plus B1 plus D1 equals 180 degrees, interior angles of a triangle. So then A we have, that is 59, and B1 and D1, they are both the same angle. B1 equals D1 because angles op equal sides, okay, which means that B1 equals D1. So then we had A is 59 degrees, B1 plus D1, we can just call them X plus X, and that equals 180 degrees. So then 180 minus 59 is 121 degrees, and X plus X equals 2X, and then we can go ahead, divide this by 2, divide that by 2, and X equals 60.5 degrees. And reminded that X was B1 over here, so therefore B1 equals X equals 60.5 degrees. And then at this stage, 7.2.2, they're asking for the size of angle O1 over there. So this is a 4-mark question, and this is the last question in the section. So we just calculated angle B1 here. These are all follow-on questions for a reason. We worked with A, got B1 over here, and now we need to get into the circle. So the easiest way to do that, like we mentioned, we used tans from the same point. There's also tan perp rad, which we haven't spoken about, which means this guy is 90 over there. And then the other thing to keep in mind is tan chord theorem. Whenever we have a tangent and we see some sort of triangle, like DBC, for example, where all 3 points are on the circumference, it means we can use tan chord theorem. And the way that we do tan chord theorem is we jump into this whole triangle and then we jump across to the further side. The reason this works regardless of whether you're taking it from B1 or D1 is that when you jump in and you go to C, from here you jump in and you go to C as well, which means C over here is 60.5 degrees because of tan chord theorem. Okay, that just earned us 2 marks, 1 mark over there for our angle, 1 mark over there for our reason, and then we're just 1 move away from O1. One thing to keep in mind when we always have an arrow, something that looks like this, for example, is angle at center equals 2 times the angle at circumference. The fact that they both share dB and we can trace from B to O and D to O and also D to C and B to C means we're dealing with angle at center equals 2 times angle at circumference, which means O1 is just 2 times 60.5, which means it is 121 degrees. And the reason, once again, is angle at center equals 2 times angle at circumference. And that is our final answer for O1 over there. Cool, guys. So question 8, we have 8.1 here. In the diagram below, A, B, and C are points on the circle with center O. Okay. Prove the theorem which states that AOC equals 2 times angle B. So this is a 5-mark question and we have to prove this theorem. This is quite a common one. They do enjoy asking it, and it is grade 11 one, so it's very likely that they will ask it in your June paper. So what we have to do in order to prove this is construct a line from B through O. And we have to write the fact that we construct a line. So we say construct line through O from B. And this creates O1 and O2 over there. We did this construction because we are dealing with 2 triangles. We're dealing with triangle BAO and triangle BCO over here. And we're dealing with them separately. So the first point we have to do is we have to say AO equals OB. This is because radii. Because AO and BO are the same length, it therefore means that this angle here is the same as that angle there, which means OAB equals OBA. This angle equals that angle, and we're going to call them X. And our reason is because angles op equal sides. So we know that this guy is X, this guy is X2. And then last move for this triangle, BAO, is that O1 equals 2x because of exterior angles of a triangle. So this guy plus that guy equals this guy over here. We can do interior angles of a triangle and then do angles on a straight line, but we can jump straight to it with the exterior angle of a triangle, that this x plus that x equals O1. So therefore O1 equals 2x because of exterior angle of triangle. So at this stage, OBC is exactly the same. We just have to basically repeat this whole formatting here, just in triangle OBC. So I'm going to do it quickly, saying OB equals OC, radii is our reason. Now that we have that, therefore this angle B here equals angle C here equals Y. We can't assume that it is also X here because we don't know how this line intersects this angle B, whether it bisects it or not. So we're going to call this guy Y. So therefore OBC equals OCB equals Y. So we have a Y there and a Y there. And once again, that is the same reason as here. Angles op equals sides. Great. And then once again, O2 equals 2Y over there because exterior angles of a triangle. Great. We're almost done. We're in the finishing stage where we're just setting up the equation in terms of X and Y, proving that AOC equals 2B because ABO plus CBO equals X plus Y over here. But then we're going to do the same thing here, that AOC equals 2x plus 2y. So we have proven both of these already, and therefore AOC, if we were to factorize the 2 out of here, we would say 2x plus y over there, and therefore this guy, AOC, is 2 times the size of this whole angle here. And we can just finish our statement by writing this final answer, that AOC equals 2B. And we have just proven that angle at center equals 2 times angle at circumference, earning ourselves 5 marks. Great. So 8.2 in the diagram below, BC is parallel to FD over there, okay? And C3, this guy over here, equals X, and then AFB and EFC are straight lines. So 8.2.1, determine giving reasons for other angles that are equal to X. So 4 other angles that are equal to X. Off the bat, we have tangents from the same point. So therefore, CD equals AD. Because of tans from same point, therefore A3 also equals C3 because angles op equal sides. So we have one angle here that makes this statement true. We can then go ahead and prove angle B equals A3 over here because tan chord theorem. So we have a triangle ABC over there, and therefore this angle A3 equals angle B over here. So we can write A3 equals angle B because of tan chord theorem. Okay, so now that we have that, we have B as well. And then from B over here, if we were to look at BCEA, we have a bow tie going on there, which means that our angle E relative to our angle B here is exactly the same because of angles from same segment. So B equals E, angles in same segment. And then we're almost done. The only other thing missing and that we haven't used is the fact that these lines are parallel, which means that B over here equals angle F2 over here because we have an F over here. These parallel lines, therefore B equals F over there. So we have angle B equals angle F2 because we have corresponding angles. And then we just have to write the parallel lines. We have FD is parallel to BC. So those are the 4 other angles that are equal to X. We have A3, we have B, we have E, and then we have F2. Okay, and then at this stage, it says prove that AFCD is a cyclic quadrilateral. Okay, so they're saying AFCD over here. So if we were to connect them, it would be something like this, for example. So whenever we're proving a cyclic quadrilateral, there are a couple ways to prove it. We can either look for a tan chord theorem, so some sort of exterior angle going into a triangle and those two equaling to prove the converse tan chord theorem. We can also look for converse of opposite angles of a cyclic quad supplementary. If we can prove 180, then we can prove that, but we don't have any angles, so we won't be proving that. Another very common one they like to ask is the converse of the angles in same segment. So if we are in AFCD over here, here, and we are trying to prove that a circle could be drawn perfectly around those points, as if they were all touching the points on the circle, we can then go ahead and prove the converse of angles in same seg. So we're looking for a bow tie, and the bow tie that we're looking for is over here. Because over here, based off of this previous question that we just calculated, getting 4 other angles that are equal to x, we know that f2 is equal to x, and this original c3 is also equal to x. And these two guys are both angles in the same segment. So we can just go ahead. It is only a 2-mark question, which means there wasn't a lot of work for us to do. This was the follow-on question to help us prove this question. We can just go ahead and say f2 equals c3 equals x. This was proven already. And because of that, therefore AFCD is a cyclic quad. And our reason for this is converse angles in same seg. And we have just proven that AFCD is a cyclic quadrilateral for 2 marks. And now we're on 8.3. This is the last question of this section. So 8.3, in the diagram below, AC is the diameter of the circle with center O. So we have a center, very important. AC is produced to P, so it's just an extension of a straight line. B1 plus B2 equals 127 degrees, okay? And P equals 16 degrees over here. So it's saying show giving reasons that BP is a tangent to the circle at B. So this is a 5-mark question. It looks like a tangent, but we can't assume it is a tangent here. So in order to prove a tangent, we have to look for some sort of tan chord theorem, considering we have a triangle inside our circle. So the first move we want to do here is note that our AC is our diameter. If ever we have a diameter, we can cover up half of the circle, which means we have angle in a semicircle. It means we have a right angled triangle over there, which means this is all shaded. We have an angle in a semicircle, and that means this B1 over here is 90 degrees. So we're going to say B1 equals 90 degrees, angle in semicircle. So we have 90 degrees here. A reminder that we're trying to prove the converse of tan chord theorem, meaning that we're trying to prove that B2 over here equals angle A over here. So if we know that B1 equals 90 degrees, it means that B2 is the remaining portion, which means we can take 127, subtract 90 from it, and we'll have B2. So this is just working out. There's no reason here apart from the fact that 127 was given to us. So therefore 127 minus 90 equals B2, and B2 therefore equals 37 degrees. Okay, so that means if B2 equals 37, we're trying to prove that A over here equals 37 as well. And what we can do, considering that we knew that this whole thing is 127, we can look inside triangle ABP over here, and we can do interior angles of a triangle. Once we've done interior angles of a triangle, we'll see that this angle here, A, also equals 37 degrees, and then because those two angles are equal, B2 equals A, then therefore we can prove that it is a tangent using the converse of tan chord theorem. So therefore A plus P plus B equals 180 degrees. This is because interior angles of a triangle. Cool. And then A is what we're trying to figure out. But then P equals 16. That was given to us. B as a whole equals 127. That was given to us. And this equals 180. Then we can go ahead, add up the 16 and 127, take them over and subtract them. So 180 minus 127 and minus 16 equals 37 degrees. And that is great for us considering that B2 equals 37 degrees and A also equals that now. So therefore B2 equals A equals 37 degrees, and therefore BP is tangent because converse tan chord theorem. Okay, and that is our final answer, and that just earned us 5 marks and 17 marks for this whole section. So we're on question 9, and this is the last question of the paper. This is a similarity and prop theorem question. Okay, so 9.1, in the diagram below, PQ equals QR equals RS, and VR is parallel to TS. So 9.1.1, they set up to help us with 9.1.2, determine the value of TV over VP. So what we can do, this PQ is X, this QR is X, and this RS is X, which means that this portion here represents 1X 1x, and this portion here represents 2x over there, which means we can just go one move. We can write TV as x over VP as 2x over there, and therefore cancelling out the x's, we have 1 over 2 is the value of TV over VP. Okay, and we just earned 1 mark over here for determining the value of TV over VP, and then we just need 1 mark for our reason saying prop theorem. So then 9.1.2, it says determine the value of the area of triangle PQV. Okay, we got PQV over there over the area of triangle PST over here. So this is a 5-mark question, and what we need to do is use our area of a triangle formula, but not the half base times perpendicular height. We need to use our trig in triangles area formula, where we have half AB sine C. This is very common to use this formula in a similarity section. Okay, so I'm going to go ahead and set up the area of triangle PQV so long. So we're going to take half VP over here. The other side's going to be PQ over there. So we're going to go half PV times PQ multiplied by sine of the angle in between these two sides, which means it is angle P over here. So we're going to go sine P. The reason we want to work with sine P specifically is that it is a common angle in this triangle VPQ and also in triangle TPS, which means that it is going to cancel out quite nicely for us. So if we then go ahead and set up the area of triangle PST, we have half as well, because that is our formula. And then what we're working with in PST, PT over here times by PS over there. Cool. And then once again, it is this whole side here and this whole side here, which means we're working with sine of P over here as well. So that means we can go ahead and cancel some things along. There's no reason for this. This is just the setup so that we don't have to write any words here explaining why we've done this. So we can cancel our half and our half because they're exactly the same. So we can cancel them, and our sine P as well. So that means we have PV over PT multiplied by PQ over PS. The reason I split them up was because these sides over here, PV over PT is just one side of our triangle, and PQ over here is this guy over PS over there. That is the other side of our triangle, which means at this stage to use 9.1.1's information as far as how we set up our triangle in terms of x, we can then go ahead and plug in the values for PV and PT, because PV equals 2 or 2x, and then PT over here, PT equals 3 or 3x if we want to keep the x's in. Either way, they're going to cancel each other out, the x's. PQ here is 1 or 1x, and then PS over here is 3. So then at this stage, there were no reasons for these guys specifically. We can just times top and top and bottom, and then we'll have a final answer of 2 over 9 there, and that'll be the value of this area of triangle PQV over the area of triangle PST, and that will earn us 5 marks. And then question 9.2, in the diagram below, B, C, and D are points on the circle, and ADC is a straight line. AB is a tangent to the circle at B. Tangent, always important. Prove giving reasons that triangle CBA is similar, so the angles are exactly the same, to triangle BDA. So this is a 4-mark question. So we have triangle CBA over there and proving that it is similar to triangle BDA over here. So I'm just going to rewrite what they've given us. So in triangle CBA and triangle BDA. So these are the two different triangles that we're working in. Okay, so now that we know which two triangles we're working in, we have to prove the angles that are exactly the same. So they've set things up in a very specific order to help us, meaning that angle C over here is going to equal angle B here, or we need to find a way or a reason as to why that is the case. Same thing here for B and for D, cool. And then A here is the same as A over there, which means the easiest way to start is when they have exactly the same letter, because if we look in triangles CBA over here and BDA over here, this A is a common angle in both of these triangles. So we can just write angle A equals angle A, common angle. So we've just proven that for both of these triangles, which means we can then look at another pair that is corresponding. So let's start with C here and see if that works out for us. So C here and B over here. So angle C and triangle CBA over here. Okay, so we're talking about this angle over here. And then we need to prove that it is exactly the same as angle B in triangle BDA. So we have to prove that this angle B1 equals that angle C. And that is very doable, considering this is a tangent to a triangle in a circle, meaning that B1 equals C because of tan chord theorem. At this stage, we've just proven that two of the angles are exactly the same, which means that this angle here, this B and this D, are exactly the same as well because of interior angles of a triangle. So we can just go ahead and write that. We can say that angle B1 plus B2 in triangle CBA over there equals angle D over here in triangle BDA equals angle D1 because of interior angles of a triangle. And therefore, triangle CBA is similar to triangle BDA because of angle, angle, angle. And last question now for this section and this whole paper, 9.2.2, it says AD times DC equals AB squared minus AD squared. So considering we had just proven that this triangle is similar to this triangle, we now have to use that information to help us rearrange something in this format as far as manipulating our similarity. So the most common way at this stage is to rewrite the triangles that you've just proven were similar, so we can then see which sides are in proportion, because we had proven that these triangles were similar through the angles being the same, and the other criteria of similarity is that the sides are in proportion, and that is what we're dealing with over here. So we have triangle CBA and BDA. That means CB over here over BD over here are in proportion. Once again, the arrangement of the letters is very important, just like the arrangement of the angles was very important. So our CB over BD is in proportion. That also means our BA over our DA is in proportion. And then last move, CA over BA is also in proportion. So we just write triangle CBA is similar to triangle BDA as our reason to show us that these sides are in proportion. We then need to go ahead and see which of these sides in proportion, which of these pairs we have to use to set up this equation, because we only need to use two of them. So we have a BA or an AB here, so this guy is probably important. We also have an AD and a DC. Okay, so we know that we're working with this BA over DA because we have the BA over here, but the fact that it is squared means we have to look for one of these other guys that also has a BA. There's also a BA in this one over here, which means we are just working with these two guys as far as our equation, and then we can take it from there, ignoring this portion here. So if we rewrite this over here, we have BA over DA equals CA over BA. In order to get an AB or a BA squared, we're going to have to take this guy up. This is the most common move here, is to take both of the denominators up, considering we do not have a denominator here. So if we multiply the BA up top there, it means we have BA squared. And then if we multiply this DA up there, it means we have CA times by DA. At this stage, we have this AB squared over here. That's great for us, this BA squared. We also need an AD squared and a minus, and things are only multiplying here. Here's a DA, so that's an AD, that's great. And then this guy is a DC, but the CA is not in our final answer, which means we have to do something with CA. So we're going to reference the diagram to see how we can change CA over here into DC by some stretch. So we have CA, this whole thing over here, and we need a DC. A DC is living over here. That's pretty good for us, considering that AC, the CA, equals AD plus DC. That means we can just expand it. We can remove our CA and substitute the AD and the DC. So AD plus DC equals CA. So AD plus DC equals AC or CA. So we have just removed the CA and replaced it with these two portions over here. Okay, and we are still multiplying by DA over there. So this is looking good for us, because now that we have substituted this in, we can multiply each thing in. So DA times AD or DA, doesn't matter which order the letters are in. AD times AD becomes AD squared. That's great for us because we have an AD squared there. And then AD times DC over here, we have plus AD times DC C. We just FOILed this guy to both. So AD times AD is AD squared. AD times DC is plus AD times DC. And this still equals BA squared. And then at this stage, we can just go ahead and say BA squared minus AD squared. That is what we have here. AB squared minus AD squared. We can just rearrange the order of our BA squared, saying that it is AB squared. So AB squared minus AD squared equals AD times DC. And that is what we have here, AD times DC. And that is our final answer. There are no other reasons here. This was all just working out and using the fact that these triangles were similar, using these sides in proportion, and did the correct substitution in order to set up this final answer in terms of the setup that they asked for. Great. That is the last question of this section. 4 marks earned, 15 marks for this whole section, and that is the entire paper. Great job, guys. Let me know if there are any questions in the comments below, and then I will see you in the next video.